Hey, what's going on, everyone? Welcome back to our structural analysis sequence. And in this video, we're going to do an example problem using the slope deflection method. And the slope deflection method is typically the first displacement method of structural analysis that you learn in a first course in structural engineering. And really, the approach for a displacement method is to come up with some sort of load displacement relationship, and then solve for displacements first, then calculate the forces or the internal loading, and then apply basic statics to get any other loading or shear diagram. But what we're going to do here is the slope deflection method, and here's the slope deflection equation. Hopefully you've seen this equation or this form of equation before. In some textbooks, sometimes they use the symbol AB instead of IJ, or NF instead of IJ, and really all that means is near and far. But really here, this slope deflection equation is just a moment rotation relationship plus fixed end moments in IJ, and I'm going to show you how to use that here. And here's the problem that we're going to look at. It's a continuous beam ABC. At point A, it's fixed. B, it's a roller. And C, it's fixed. I've got a concentrated load of 10 kilonewtons at midspan between A and B, 1 kilonewton per meter uniformly distributed across BC. And the way I'm going to approach this problem to calculate the shear moment diagrams, and this is my general approach for a slope deflection method slope deflection problems, is determine unknown displacements, which is really to determine the number of kinematic degrees of indeterminacy. And then I'm going to blow up my structure, which really means I'm going to draw it in a blown up way, I guess. And then here, the fixed end moments is something that I want to calculate for each member. Apply the slope deflection equations, 2 slope deflection equations per member. Look at equilibrium, and then just do basic statics to look at to find all the other internal loads. So let's get to it. The first thing that we want to do is this unknown displacement, which is really the number of kinematic degrees of indeterminacy. And that's really all the ways that this structure can move. And if you look at point A is fixed. It can't move anyway. All right, so point A is stuck. Point B might be able to move left or right, but if we neglect axial deformation, so we're going to assume axial def is negligible. And this is typical for most first course in structural analysis, that you can assume axial deformation is negligible. So really, even this point B could actually move left or right, but here in this case, it will only be allowed to rotate, and the reaction from BY, or this roller, does not allow it to move up or down. And then point C is fixed too, so this thing can't move anywhere. So this really has this NOK, the number of kinematic degrees of indeterminacy, is 1. And really what this suggests is that you just need one equilibrium equation later on to solve this problem. So the next thing to do is to blow up this structure. So here, to blow up the structure, and when I say blow it up, so this is really just a schematic that you're going to redraw. And here, what you want to do is draw it so that I have, bam, here it's fixed. And you may want to fast forward some of this right here. It's fixed here. So it's as though I were making a cut here, 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 and here, and redrawing my structure with all the gaps. So here I have this first cut, then I have my member here, then I have this next with the roller like this, and then I have my member here, and again with the roller, fixed end here at point C. And this is, this is point A, here's point B, and here's joint C. Just in general, for my reactions, I'm just going to write here, I have a reaction at A over here, and a reaction at C over here, and I can draw that in any direction, okay? Now, I have the loading of 10 kilonewtons here, and a distributed load like this here, like this, okay? And what I want to do is draw the internal moments here in each of those, okay? So in this schematic, I only need the internal moments. But one thing you want to pay attention to is positive sign convention. And in the slope deflection equations, or the way that they were derived, a positive moment at the end of a member is clockwise. Okay, so it doesn't matter which end you're on, but this would be, if this is end I, and here's end J, this is MJI. This is a positive moment here, and this is MIJ right here. And so for me, in each member that I've cut, I want to draw on the member, again, not the joints, on the member, I want to draw my internally positive moments according to this sign convention. So here, MAB would be here clockwise. MBA would be, again, clockwise here. And then here, this would be MBC. And here would be MCB. And this is really important. If you don't do this right, you're not going to get anything right. Okay, and that's just the way it is. And then from there, you to go to the other side, just apply equal and opposite. So here, this is again MAB, equal and opposite. Here is MBA, equal and opposite. Here is MBC, equal and opposite on the joint, and MCB, equal and opposite on the joint. And there is my blown up schematic. The next thing I think in my process is to determine fixed end moments. So here 3 are fixed end moments. And this is where you would use tools in the, on the inside cover of your books, or just Google fixed end moments, and you'll see a bunch of drawings of fixed beams, something like this right here. Fixed beams right here, and with some generic value for a load like P here. And what you'll discover is that it'll tell you, oh, the moment here has a magnitude PL over 8, and this has a magnitude PL over 8, whereas here, this is the length L. And this would be for the case where I have something applied directly at midspan. And it tells you what these moments are at the ends of a fixed beam. And then you will look in another diagram, and you might see here a fixed beam with a uniformly distributed load right here. And again, you can fast forward this if this is all redundant to you and you've heard this before from whatever faculty member you're learning from. But here, this is L right here, and this right here, this moment right here is WL squared over 12. L squared over 12 on each side. Now you got to be careful. Sometimes they put a little negative sign here, and you just want to be cautious about interpreting that negative sign correctly. This is the correct direction of the moment in this PL over 8. And the negative only comes into play depending on how it relates, how the fixed end moment relates to your beam end right here, the way you've drawn MAB, for instance. So for instance, now, if I'm looking at the fixed end moment for AB here, that suggests the fixed end moment at this location of member AB with this concentrated load. This fixed end moment goes PL over 8 in this direction. This would be counterclockwise. So really that's opposite of MAB. And so I would write negative PL over 8, which in this case is PLAB, which would be negative 10 kilonewtons times 10 meters divided by 8. And that tells me that the fixed end moment for AB is minus 12.5 kilonewton meters right here. The fixed end moment for BA, which is on this side, look at MBA, the way I've drawn it, is in the same direction as this right here, the fixed end moment on the right here for a concentrated load, PL over 8. So that's positive. This is positive PLAB over 8. And that is just a plus 12.5 kilonewton meter. I'm going to do the same thing for member BC over here, this member BC. And here for member BC, I would have fixed end moments for BC. On this end, again, this WL squared over 12 is in the opposite direction of the way that I have MBC drawn. And therefore, this is minus WL squared over 12. And this, if you plug and chug with 1 kilonewton meter and L of 20, hopefully this is right, it's negative 33.33. Oh, I'm going to go to 3 significant figures. Don't judge me. Shoot. The only people who aren't judging me right now are probably rocket scientists. But why would they watch this video? Anyway. All right, so here, minus 33.333 kilonewton meters. And the only reason I'm putting that is because I did this problem before, and I just need this level of accuracy to make sure my shear moment diagrams are consistent. But here, this FEM CB is, as you can imagine, positive because this MCB is in the same direction as this WL squared over 12. So this is WL squared over 12, and this is plus 33.333 kilonewton meter. So now we're going to do our slope deflection equations, and gosh, it's already been 10 minutes. So let's do that in part 2. This example takes a long time, right? These problems take a long time. So I'll see you in part 2.